This question is about sodium and some of its compounds. Use your knowledge of structure and bonding to explain why sodium bromide has a melting point that is higher than that of sodium and higher than that of sodium iodide. So I think the first thing that we need to do is look at the structure and bonding in each of these three compounds and element, sodium. So if we start with looking at sodium. So sodium is a metal. So sodium has a giant metallic lattice structure. And its bonding would therefore be the strong forces of attraction between, because it's a metal, between positive sodium ions and delocalized electrons. So those are strong forces of attraction. So that's the structure and bonding in sodium. And then we've got sodium bromide and sodium iodide. Now they're both ionic, so I'm going to group those two together for the structure and bonding part. Am I spelling this all right? Are both giant ionic lattices with strong forces of attraction between, and in this case, because they're ionic, oppositely charged ions. So now we need to look at the differences in their melting point. So why is sodium bromide higher than sodium? Well, we must be able to say then the ionic bonding, if it's a higher melting point, it must have stronger force of attraction. The ionic bonding in NaBr, sodium bromide, is stronger than the metallic bonding in sodium. So that's our first comment there. And then it asks us why sodium bromide is higher than sodium iodide. Now we can do a little bit more explaining here, because they're both ionic, so we might think that they're both the same, but why is sodium bromide higher? So the force of attraction between oppositely charged ions in NaBr is stronger than in NaI. And why is that? Because Br minus ions are smaller than I minus ions, so have higher charge density. And that increase in the charge density, they're the same charge but smaller, so they have a higher charge density and therefore they form stronger attractions. And now we've answered all the parts of the question. We've explained the structure and bonding in each of the lattices, and we've explained which bonding is stronger and why the ionic bonding is stronger in NaBr than in NaI. So the next part of the question says when 250 milligrams of sodium, which is our Na, is added to 500 centimetres cubed of water, a gas was produced. So we've got a mass, but it's in the wrong units because mass has to be in grams. We've got a volume of water, we've got a temperature, and we've got the gas constant. And we're being asked to calculate the volume of gas formed at 101 kilopascals. That's the pressure. So first of all, we have to write an equation between sodium and water. So metal plus water makes the metal hydroxide, and the gas is hydrogen. And we need to balance that equation. So to balance that equation, there's one sodium on each side at the moment, there's one oxygen on each side, but there's 3 hydrogens on the right and only 2 on the left. So I could either put a half in front of the hydrogen gas, or I could double everything else. Now the question is asking us about the volume of gas, and the hydrogen is the gas. And we've been given the mass of sodium. So the first thing I'm going to do is work out the moles of sodium, the mass over the MR. So 250 milligrams, turn that into grams, divided by the MR, 23. So we type that on our calculator, and we see that we get 0.01087 moles of sodium. But because we want the volume of gas, we need to know the moles of gas, and in this case the gas is the hydrogen. So we need to work out the moles of hydrogen, and that would be the moles of sodium divided by 2, half the moles of sodium. So I'm just going to press divide by 2 on my calculator, and I get 0.00543. So now that I know the moles of hydrogen, I can use PV equals nRT, which I can rearrange to say V equals nRT over P. So the moles of hydrogen are 0.00543. The gas constant is 8.31. The temperature was 25 degrees C, but I need to add 273 to that to get it into Kelvin, so 298 Kelvin. The pressure is 101 kilopascals, but I need that in pascals, so I'm going to times by 1,000. This will give me an answer in meters cubed, so I'm going to take my calculator and type this in. And I'm getting 1.33 times 10 to the minus 4. But remember that this answer is going to be in meters cubed for a volume of a gas. And to convert to centimetres cubed, I need to times by 1,000,000 times by 1 times 10 to the 6. And if I do that, I'm going to get 133 centimetres cubed. The next part of the question asked me to calculate the concentration of sodium ions. Now if I go back up to the equation, the sodium ions are in the sodium hydroxide. So think about this, this is actually a sodium ion and a hydroxide ion. So if I know the moles of sodium, I know the moles of sodium ions. So the moles of Na plus ions is the same as the moles of sodium I worked out right at the beginning here, 0.01087. And the concentration of sodium ions, they were in the water, so it's moles over volume of water, not the volume of gas, but the volume of water. So 0.01087, and this is where I'm going to use the 500 centimetres cubed. Remember that concentration is in moles per decimetre cubed, so you convert your centimetres cubed to decimetres cubed. And if you do that calculation on your calculator, you will get 266.5 or 260. Oh, I think I've typed it wrong. Let me just repeat that. If you don't get, you get 0.02174. Sorry about that. Always check your calculations. 0.0217. Last part of this question asks us about shapes. Sodium reacts with ammonia to form the compound NaNH2 that contains the NH2 1- ion. So let's have a look at this. We've got nitrogen in group 5. We've got 2 hydrogens, each bringing 1 electron, so that's 2 electrons, and we've got a minus charge bringing another electron. So in total we have 8 electrons around the nitrogen, or 4 pairs, but we've only got 2 things to bond to, 2 hydrogens to bond, so we must have 2 bond pairs and 2 lone pairs, which means this is the same shape as water. So we have that V shape based off the tetrahedral 109.5, but squished down. So we're going 109.5 minus 2.5 for each lone pair, so 104.5 as our bond angle. So 104.5. So what's our justification? Well, let's have a look at what we did. There were 4 pairs of electrons around nitrogen. Electron pairs repel to get as far apart as possible. That would have been 109.5 if they were as far apart as possible. 2 lone pairs, 2 bond pairs. So we've got some lone pairs. So we need to say lone pairs repel more than bond pairs, reducing the angle.